Hi, you're with Christian from AMC, and today we're discussing Module 8, Electrical Theory. We're going to be talking about electricity, what it is, how we produce it, and what do we do with it. And just from the outset, I'd like to explain that a lot of students struggle with this particular topic, and also I'd like to encourage you that if you're one of those, and you can understand other systems, mechanical, hydraulic systems, then electrical systems are no different. They're just another system.
Hi, welcome. This is Mark from SimpleElectronicsCourses.com. Today I wanted to talk about how electricity works, what it is, where it comes from. Electricity is defined as the flow of charge. Now there's different kinds of charge, but the one we're going to be worried about is electrons and the flow of electrons. That's what electricity is, especially when we're dealing with electronics. Here's a picture of an atom. Now an atom is made up of protons and neutrons and electrons. Electrons are the things swirling around the outside. The protons and neutrons are the particles that are in the middle. So what we're worried about are these electrons swirling around the outside. They don't really go in nice orbits like that. It's much more like a bunch of mosquitoes swarming around your head on a hot Minnesota evening. Here's a picture of all the different kinds of atoms there are. Now, the kind of atom is determined by the number of electrons and protons and neutrons that are in it. If we look here, we'll see that we have an H here for hydrogen and an O for oxygen. I'm sure you've heard of water referred to as H2O. Well, if you take two hydrogen atoms and one oxygen atom and get them to stick together, that makes up water. So everything we have around us is either a combination of atoms or just atoms by themselves. All of these atoms have electrons, and some of them hold on to their electrons a lot stronger than other ones do. The ones that don't hold on to their electrons real tight are called conductors. The ones that do hold on to their electrons real tight are called insulators. So let's say you have a piece of wire and you push an electron in on one end, and because we're dealing with conductors, each atom will push the electron, bump it over to the next one, which bumps it over to the next one, which bumps it over to the next one. Pretty soon we've got an electron that can come out the far end of the wire. Now, if we stop and look at how many electrons go past a particular point, if we've got this number, this huge number of electrons going past a particular point per second, that's referred to as 1 amp or 1 ampere. That particular number, if you know any chemists, you can impress them by telling them that you know Avogadro's number, which is 6.02 times 10 to the 23rd. That's the number we're looking at. And that's what current is. When people talk about amps or current in electricity, it's the flow of electrons. And how many electrons are flowing is what's used to define current. So how many electrons go past the point? Well, that's current, but that also depends upon how much force there is. The more force you have on the electrons, the more are going to go past. That force is called the electromotive force, or EMF. It's also known as voltage.
So just recapping from what Mark said from Simple Electronics, courtesy of YouTube, our electron flow is basically the electrons moving from one atom to another. So the nucleus is positively charged in the atom and the electrons negatively charged, and they move from one atom to another, and that is the flow of electrons, and that is what electricity is. So whenever there's one atom is moved, one electron is moved from an atom, it's deficient in an electron, and because the proton is positively charged, then this one attracts the negative charge of an electron, and that propitiates this flow of electrons. Alright, so how do we get the flow of electrons to occur in the first place? Well, we get electrons excited. How do we excite electrons? We use magnetism. So, okay, you'll probably remember from high school science there's a north and a south pole of a magnet, and there's these invisible lines of force, magnetic lines of force, which flow from north to the south pole, okay, in this direction. And it was discovered that when we take a conductor and we pass it through the magnetic lines of force, then we have a charge of electrons. We get electrons excited, stimulated. Alright, so a better way, rather than oscillating a conductor through the magnetic lines of force, we use rotational force. So we take two magnets, a north and a south, and I take a conductor and I'm going to shape it into a loop, and I'm going to rotate it. So I'm going to rotate it 90 degrees and draw the same loop orientated 90 degrees. Alright, and this is basically what the inside of our alternator looks like. We'll go into a little bit more detail in the next module on alternator construction, but essentially I'm just going to draw a graph with timeline as the x-axis and voltage on the y-axis. This is 0 volts, and so if we start in this dotted line position, this is when the conductor is furthest from the magnets, and it starts off at 0 volts, and as we rotate it closer towards the magnet, then it starts increasing in value until we reach this orientation, and in that position where it's closest to the magnet we have the highest strength and it hits a peak. And as we keep rotating a further 90 degrees, we find that it drops back down to 0 volts again. And as we continue to rotate, and this sends the electrons flowing in one direction, and as we continue to rotate, then it increases in strength as well, but it flows in the other direction. And so we end up with what we call a sine wave or sinusoidal wave, and we have when it's flowing in this direction, then it just reverses the direction of flow in the conductor, so it moves from that direction and changes back and goes in the other direction. So in reality, we've just created AC with this system, alternating current. And alternating current goes in a positive and then a negative cycle like this. In reality, what it is in a conductor, it's just flowing in one direction and then another, backwards and forwards, backwards and forwards. So it's alternating in direction. In this presentation, I'm going to be working through some of the problems that are in your learner's guide. Then you need to go to the workbook and work through some of the examples. So some of them have answers there for you, and they're so that you can check on your own work. And then there's assessment items which you need to fill in the workbook which don't have the answers and that you'll be assessed on. First up in our calculations, we have Ohm's law. Now, Ohm discovered this particular formula where voltage equals current times resistance. And as you know from having done module 1, 2 and 3, we can rearrange that formula in 3 different ways. So if we need to find voltage, or if we need to find the current, then that would be current equals voltage divided by resistance. Or if we need to find resistance, that would equal voltage divided by current. Okay, so 3 ways of doing that formula, rearranging that formula. And look, if in case you're struggling with it, then there's also a method we can use to remember this. V equals IR, we've got a divider by sign here, invisible. So this can help us rearrange that formula 3 different ways. If we need to find voltage, then we cover it up and we have I times R. So V equals I times R. And if we need to find the current, we just hold our finger over that and it becomes V divided by R. And if we need to find resistance, hold our finger over the R and it becomes V divided by I. Okay, let's launch into our learner's guide. Has some examples there and I'm just going to run through those. So the first one there in Module 8 activity, our worked example, number 1, it says here that a circuit supplied from a 24 volt battery, so voltage equals 24, draws a current of 6 amps, and it says what is the resistance of the circuit. Okay, so we always write down what we know, what we need to know, and find a formula. So resistance equals V divided by I, 24 divided by 6, so that would be resistance of 4 ohms. Alright, question 2. It says if the current measured flowing into a circuit is 20 amps, current equals 20 amps, and the resistance of the circuit is 12 amps, then what is the supply voltage? What we know, what we need to know. Find a formula. V equals I times R. So 20 times 12, and we have 240 volts. Okay, next one, number 3. Question number 3. A voltage of 24 volts is supplied to a circuit containing a resistance of 48 ohms. What current would flow in the circuit? Okay, what we know, what we need to know. Find a formula. I equals V divided by R. So that's 24 divided by 48, and that gives us 0.5 amps. First up, we're going to look at doing calculations in a series circuit, and we're going to use a bit of Ohm's law, but we've also got to look at our resistances. So if we have resistors or loads in series, and we call this R1 and R2, they're obviously in series, then our total resistance equals R1 plus R2 plus however many resistors we've got. So all well and simple, very straightforward. So we're going to have a look at that in terms of a problem in our learner's guide. So the example here is there's 2 resistors. The resistance equals 25 ohms in each, and they're supplied from a 250 volt system. So it asks us to calculate the current flow in the circuit. Alright, so we've written down what we know, what we need to know. First of all, we've got to find the total resistance. So total resistance equals R1 plus R2 equals 25 plus 25 gives us 50 ohms resistance. Straightforward. And now we just substitute into our formula for current equals V on R, and we've got 250 volts divided by 50 ohms, so we end up with 5 amps. This example is written for you in your book. Now that one's all well and simple. Now we look at parallel resistors or loads in parallel. So if I have R1 and R2 and I want to find what the total resistance is in a parallel circuit, has an inverse relationship where 1 on RT, or the inverse of total resistance, equals 1 on R1 plus 1 on R2 plus. Okay, so let's look at how that looks in terms of an example. We'll calculate that. So using the same sort of figures, this is also a problem it's in your book. So, but it asks to find the current of a circuit consisting of two resistors in parallel, where the resistance equals 25 ohms and it's supplied by 250 volt supply, and we need to find the current. Okay, so because they're in parallel, I'll just draw a little sketch again. R1, R2, so they have the same value resistance, and we said that for parallel, total resistance RT equals 1 on R1 plus 1 on R2. So 1 on RT equals 1 on 25 plus 1 on 25, and that equals, so here we go to our calculator, and we want to find the inverse of 25, or 1 on 25, so I can type in 1 divided by 25 equals, that's 0.04, or I can go type in my 25 ohms and see this button here, it says x to the minus 1. On some calculators it says 1 over x, or x to the minus 1. So that button there, if I hit that now and say equals, will give me that same answer, 0.04. So 0.04 plus my 25 inverse, and it'll give me 0.08. So that was 0.04 plus 0.04 gave me 0.08, and then that's 1 on RT. Now I want to find what RT is, the total resistance. So I hit that button again, yep, and hit equals, and it gives me 12.5 ohms resistance. Now you'll notice that in our first one we had two resistors in series, and the two resistors in series, the RT equal 50 ohms, but in parallel it's 12.5 ohms. So this is the interesting thing about resistors in series, is that RT, the total resistance, will be smaller than the smallest resistance. So we had 225 ohms resistance, but the total resistance is 12.5 ohms. It's because there's a lot, because we're spreading out the flow of electrons through multiple resistors, it's an easier path of flow. So it has, the total resistance is less than the lowest resistor. Oops, you couldn't see any of that. The total resistance is less than the total resistance because there's much greater spread of electron flow through when we have multiple resistors in parallel. Okay.
Perhaps the greatest achievement of modern man is the ability to harness the power of Zeus. The importance of controlling electricity is easy to take for granted, but electricity is why doing stuff at night is so easy, and at this point, it's what keeps the first world first. But what should be the second greatest achievement of the industrialized world gets even less attention. It's the ability to put Zeus in your pocket. The battery is the silent, unsung hero of modern man, and batteries are everywhere. Just go to a concert. The ability to store up some energy, walk around with it, and use it when you need it has had a profound effect on our lives and our cultures. The battery is what gives us instant images, and that has made things possible like internet memes and revolutions. There are many different types of batteries, but they all pretty much work the same. Let's look at a cell phone battery. Now, to understand how a rechargeable battery works, you need to know a little background.
The electron.
This is an atom. The inside has a clump of positive charged particles in it called protons. The outside is a buzzing cloud of negatively charged particles called electrons. And electrons are the key to electricity. The movement of electrons is what makes the lights go on. So how do you get electrons to move through a wire if they're happy just buzzing around as part of an atom? Well, it turns out that electrons just want to be happy. And for electrons, happiness is being at a lower energy level. Think of it like this. Let's say a high energy level is like working at a high stress job, and a low energy level is like sitting at home stress-free. If your boss said, "Hey, do you want to work from home?" you'd do that. And if your boss said, "Hey, do you want to stay at home and still get paid for not doing work?" who wouldn't do that? Well, electrons do the same thing. For electrons, buzzing around some atoms is like working in a high-stress environment, and buzzing around others is like sitting at home and getting paid for nothing. A battery basically gives electrons a path to a happy, stress-free life, but makes them work for it, which we'll get to in a second.
The ion.
Here's the atom again. As we mentioned earlier, there's a positive charge part and a negative charge part. In a normal atom, there's balance. The number of protons equals the number of electrons. But if an electron leaves this atom, now the positives outweigh the negatives, and we're left with a net positive charge. Add electrons, and we're left with a net negative charge. These are ions. An ion is simply an atom that is no longer neutral. It has a charge because it has either lost or gained electrons. So while electrons want a low energy, stress-free life to be happy, ions just want to be neutral. And they do this by finding an opposite charge and sticking together. The heart of a battery is electrons and ions trying to achieve happiness.
The battery.
Let's look at what parts make up a generic rechargeable battery. First, you need two different materials. One that for an electron is like working 80 hours a week for an abusive boss, high energy level, and the other is like sitting at home collecting paychecks, low energy level. In other words, given the option, an electron in material A would rather be in material B. In fact, if you just put these two materials together, electrons would just hop from one to the other. They would take a shortcut. To stop electrons from taking the shortcut, you need to add a barrier that forces them to take a detour. This detour is the circuit. In other words, the thing you're powering with the battery. And finally, you need something for ions to move around in. Here's how it works. With the circuit off, electrons in material A are stuck in their high energy, high stress atoms. Out of reach and on the other side of this electron barrier are material B atoms, which would offer an easy, cushy, low energy level position. Let's turn the circuit on. Now you've offered electrons a path to happiness. Since they can't go any other way, they begin flowing through the circuit to material B. Back at material A, the atoms are losing electrons, because that's where the electrons are coming from, and they begin turning into positively charged ions. As we mentioned before, ions always want to be neutral, so these guys need to find a negative charge. So they go to where the negative charges are, in material B, where all the electrons are going. You'd think that these ions would just meet up with their lost electrons and become neutral atoms again. But unfortunately, the electrons are way happier where they are now, so the ions have no choice but to kind of mingle with the atoms of material B. So what we've got is kind of a mishmash with B atoms mingled with A ions. As the battery discharges, electrons and ions are making their way from A to B. When you can't fit any more material A ions into material B, the battery is fully discharged. To recharge the battery, you just do things in reverse. Instead of a circuit, you're putting an energy that forces the electrons back into material A. The ions then leave material B and rejoin their lost electrons, and the battery is ready to discharge again.
One of the principles of batteries is this concept of electrolytic dissociation. So when a compound is dissolved in water, it separates into ions, positive and negative ions. So here the salt is added to water, NaCl, and it's separated into negative chlorine ions and positive sodium ions. So an ion is an atom that's lost or gained an electron. So here we are with the cell construction, and it consists of two plates in a solution, an electrolyte, which in a lead acid battery is sulfuric acid. So it's a highly corrosive substance. So our battery locker needs to be able to contain a potential spill of the electrolyte. Hence, many of our battery lockers are constructed of timber and lined with fiberglass or some type of PVC. So the two plates, a positive, the lead peroxide, and a negative is a lead plate, and it's separated between those positive and negative plates, and we get roughly a bit over 2 volts per cell. So batteries are primary or secondary, and the primary battery, once the chemical charge is used up, it's disposed of, whereas a secondary cell can be recharged. And there we can see the positive plates as indicated on the left. There's a negative plate with a separator in between. And our look, there's lots of different types of batteries, but essentially the main types we've got our starting batteries, and they have a very loose construction, loose weave, so they can give off a very rapid discharge of electron flow. They can easily draw 600 amps for a very short duration, as opposed to our house batteries or emergency batteries, which can give off our charge at a much slower rate, but essentially we can draw those batteries down a lot lower in charge without destroying the battery, whereas a starting battery, if we drain them completely flat, then it's going to be destroying the battery. Okay, we've also got two categories, lead acid and our alkaline or NiCad batteries. So we're focusing more on our lead acid batteries, and as we said before, they contain sulfuric acid, but they also release a gas, and this gas is highly explosive. What gas is it? You guessed it, it's hydrogen gas, lighter than air, very explosive, so we need to take a lot of precautions. So hence we never smoke around batteries or use naked lights, allow tools to touch the battery terminals. They need to be safely stowed, as we said, and they need to be able to vent. So we never leave battery caps off, ignore irregular readings, we'll talk more about that. We'll mix lead acid and alkaline battery tools, fitting and removal. So don't touch the positive and negative terminals or will cause sparks, and it's full of hydrogen gas. Okay, here's what happened on a vessel with where a cadet was doing some grinding on the door, the watertight door, and the hydrogen gas exploded and knocked him off the deck and into the water, and his body was never recovered. So a lot of accidents occur with batteries, so please take precautions. We also need to test our batteries periodically as part of our routine maintenance, and one way to do that is with a hydrometer. Of course we can't do this with fully sealed batteries, but if we're able to get to the electrolyte, we just unscrew all the caps, test each cell, squeeze the bulb of the hydrometer and allow the liquid to be sucked up, and then we can read off the state of charge. So the state of charge relates to the specific gravity, and basically we can follow whether it's in the red green zone or not, but here you are. It should be, to be fully charged, it should be around 1.225 specific gravity, and there we are. So we just read off, and as I said, it's normally a red, green or white zone. But if we keep a battery log of those, we also measure the voltage across the terminals, and we can keep a log of it until when one battery is starting to go. They are expensive pieces of equipment, and we need to look after those. Just a review on series parallel battery connections. So if we'll look at series first. So I always get students to draw our batteries this way. If you think of series as in, you can string them along as lights on a Christmas tree. So in a row this way, okay, for our series, and positive, negative, positive, negative. And so all we do is link the positive and negative, and if we have 12 volt batteries, then our output is going to be 24 volts. Simple enough. Alright, let's look at parallel, and I always get students to draw these one under the other, just like our parallel, parallel lines, one under the other. Okay, and again orientate the positive negative in the same way, and now we're just going to link our batteries positive to positive and negative to negative, and then our output here we're going to talk about amps. We've talked about current. So our batteries, these batteries are 12 volt 100 amp hour batteries. So we know what amps are, that's current, and hours, what this means is this battery can deliver 100 amps for 1 hour, or it could deliver 200 amps for half an hour, or it could deliver 50 amps for 2 hours. So it's the amps times the hours. 50 times 2 would give 100, or it could deliver 200 times half an hour, 0.5. So however many amps times the number of hours, so 100 amps for 1 hour. So if we look at the output of these two batteries in parallel, then the voltage is going to stay the same. We'll end up with 12 volts, but we've got two 100 amp hour batteries, so the amp hours are increased, and we end up with 200 amp hour charge from our two batteries in parallel. Okay, and then lastly we're going to look at series parallel. So our series parallel batteries, I'm going to connect 4 batteries, and I'm going to put the same orientation on them, positive, negative, and now I'm going to link my series batteries. So now I'm still going to work with 12 volt 100 amp hour batteries. Now my output here, I've got 24 volts on this bank and 24 volts on this bank. Now I'm going to connect them up in parallel, and now my output from these 4 batteries, because I've got 2 banks of 24 volt, then my output's going to be 24 volt, but I've got 2 banks in parallel here, so I'm going to end up with 200 amp hours, because this bank here is giving me 24 volt 100 amp hours. This one's giving me 24 volt 100 amp hours. So when I put the 2 in parallel, I get 24 volts and 200 amp hours. So we're going to have a look at some problems now relating to series and parallel. Okay, so just to recap on our Module 8 electrical theory, these are the things, apart from the calculations that you should have done, you should have a good handle on those. But we also need to have had an understanding of alternating current and direct current. I couldn't help myself. And we need to know a little bit about electron flow and power generation. Just the basics. We're going to go into more detail in the next module. Of course, you have to memorize these two formulas, voltage equals IR and P equals V times I. And of course, you're going to need to know the total resistance for series and parallel. resistors, and we need to have a good understanding of the following terms. You should know voltage, unit of electrical pressure; current, it's a unit of electrical load in amps; as is power, a unit of electrical load but in watts or kilowatts. We need to understand frequency. This frequency, hopefully if you're not quite understanding it, will make more sense when we look into alternators, because it's all about speed. And then we need to understand electrical resistance, measured in ohms. Okay, we also need to know a little bit about batteries. You need to understand what our emergency batteries are used for, to power what kinds of emergency devices. And then two important things with our lead acid batteries: we need to know what acid's in it. Of course, that's sulfuric acid. And we also need to know what gas it releases, which is hydrogen gas, highly explosive, lighter than air gas. Okay, a lot of people get sulfuric acid wrong. It's not hydrochloric acid, it is sulfuric acid. Okay.